Okay, so as I said, I will speak about billiards and more particularly about tiling billiards. And my goal is to introduce this class and more precisely introduce tiling billiards in cyclic quadrilateral tilings. This is the only class I will speak about today. Tiling billiards. Second, I want to present our main result, which is a proof of, I won't present a proof, but I will present the statement, a version of Novikov's conjecture. Sergei Novikov's conjecture. He has many conjectures. This one is on semi-classical motion of an electron in a uniform magnetic field in a lattice of a metal. In the mathematical terms, it's a topological story. I will tell about it more. And the third goal is to present three languages, three ways of thinking about cyclic quadrilateral tiling billiards. Cyclic quadrilateral tiling billiards. One of which is this billiard. Another one, topological approach, which you don't see probably what I'm writing. Topological approach, which is connected to the Novikov's conjecture. And another way is one-dimensional dynamics, which is dynamics of interval-exchange transformations that probably you know with flips. Tiling billiards, one could think that it's three-dimensional dynamics, but it's actually two-dimensional. I will explain it. And topological problem is happening in the three-dimensional space. So there are different languages, different dimensional languages to speak about the same object. So these are my three goals. Let's see if I manage to get them all. Okay, so what are cyclic quadrilateral tiling billiards? Yeah, sorry. Okay, so any quadrilateral tiles a plane. If you take any quadrilateral you like, even non-convex quadrilateral, you can tile a plane with it. In which way? You just have to consider a symmetry with respect to the middle of some of its sides, and then you obtain a parallel sides here. And this is a fundamental domain of your tiling. So cyclic quadrilateral is a quadrilateral which is inscribed in a circle, and it tiles a plane in the same way as I described. That would be like this, for example. And you continue this tiling. So we will have this tiling, and I will speak about a billiard in such tiling. So we continue tiling in a periodic way. And what is a billiard? We take a ball. So it's not a usual billiard in a bounded domain. Here, the billiard will have trajectories that go through all the plane, through all the tiled plane. Our ball will go in a straight line till the moment that it hits the border of a tile, and then it goes in the neighboring tile, following this peculiar rule that refraction coefficient is equal to -1. These angles have to be equal. And you continue, and the goal is to understand what happens with the dynamics. So here on the video, you can see what happens if we follow such a billiard in a triangular tiling. And let me notice that a triangle is just a degenerated cyclic quadrilateral. I want to think about them in the stock like this. And if you degenerate, if you approach these two vertices by making them stay on a circle, you will obtain a tiling by triangles. Such tiling. Okay, so how does a billiard work? I gave you a definition, and this is an animation. So you can see that a ball goes through a tiling in this peculiar way. So here we get a periodic trajectory. Surprising. So maybe I chose the parameters so well that it's a periodic trajectory, or maybe there are so many periodic trajectories that taking some random condition, I have stumbled upon a periodic trajectory. So the second is true, and I will explain you why. And it's a little bit related to the previous talk, where Dmitry spoke about potentials in which you have many periodic orbits. You perturb a periodic orbit, it stays stable. It's also the case here. So we have this integrability taste. One of the reasons that one of the two main reasons for which we have many periodic trajectories here is the folding. You see, I define the billiard in a way that if I fold along a trajectory, the tiles fold one another, and the trajectory falls into a segment in a line, right? Usually we unfold billiards, but here we have already a tiling, so we have to. Okay. So I gave you a definition of a cyclic quadrilateral tiling billiard. And I want now to speak about two other reincarnations of this system in two different aspects of the dynamical systems world. So let me start with the first, with the one-dimensional dynamics. So for now, you have to forget about billiards if it's possible, and stay with me a little bit for one-dimensional dynamics, or not, as you want. So for quite some time, half of the century, we have been thinking about how interval exchange transformations look. So an interval exchange transformation is a map which the graph of which is drawn here. You take an interval or a circle, you cut it in some number of parts, here are 4 parts, and then you exchange them, and you are interested in the dynamics of such a map. So Hinn proved that almost any irreducible interval exchange transformation is minimal. Its orbits are dense. Irreducible means that this graph is not separated into squares, independent squares. Okay, then Maser-Vich proved that almost any irreducible IET is uniquely ergodic. So this is another property of ergodic theory about interexchange transformations. Katok proves that they are never mixing, and Avila and Fournier, with techniques elaborated in the 21st century, have proven that such maps are almost always weakly mixing. So we understand how a typical interexchange transformation looks like. Now the question is, how do they look if we restrict our study in some particular subfamilies of interexchange transformations? Since we already understand a typical interval exchange, what can we say about an interval exchange taken in some class, for example, defined by some finite number of parameters? So in general, it's an open question, and it's a very interesting question for today's dynamics, and we are elaborating the tools to try to answer this kind of question. Today's talk is dedicated to one particular family. Squares, I've written here 3 reflections, but you can think of 4 reflections better. So actually 4 reflections will correspond to cyclic to quadrilaterals, and 3 reflections to triangles. So what are 3 reflections? A 3 reflection is a map from a circle to itself. You can think about an interval to itself by cutting a circle in some point. And it's an interval exchange transformation, but it not only moves intervals, but it also changes orientation. It flips them. So here is a beautiful picture of this map. The idea is from Diana Davis, the idea to draw the triangles, so you can see that the intervals flip if they do. So you take 3 intervals, and then you flip all of them, and then you make a global rotation on your circle. This is your map. So the parameters of this map are the lengths of the intervals, L1, L2, and L3. Lengths of intervals of continuity. Actually, here the map can be defined in all points, but we can forget the endpoints of the intervals. And tau, the rotation parameter. You see the tau is written on it's the image of the right end of the first interval. Tau rotation parameter. For example, if tau is 0, your map, the square of your map is identity. So the length, their sum is equal to 1, say if your circle has length 1. Okay, so we have 4 parameters, and not as usually we would have 6 parameters for the square of this map. Because you see that the square of this map is a normal interval exchange transformation because we changed orientation twice. But we don't have 6 lengths of the intervals, we only have 2. We only have 4. When I was speaking about typical interval exchange transformations, I was speaking about Lebesgue measure on the length of the intervals with a fixed combinatoric. So here we live in some subspace of our generic space, and actually many of the properties that I have stated on the first slide are not true anymore for this subfamily. So Nogueira has proven that if you take an interval exchange transformation and you make at least one interval flip, then the minimality is gone. In the sense that almost any interval exchange transformation with some combinatorics, when at least one interval flips, will not be minimal, and much stronger, it will have a periodic interval which comes back to itself after some number of iterations. So it's true also for our family, but what is surprising for our family that almost any map from our family is not minimal, as Nogueira says, but even stronger, it's not weakly mixing if it's minimal. So it's a very, very particular case. And even more surprisingly, the minimal maps in this family can only appear when tau is equal to 1/2. They all kind of go to this space, to this place in parameter space, which is a hypersurface. So R3 reflection is minimal if and only if tau is equal to 1/2. And the length of your intervals have to be very special as well. They have to lie in some zero measure set. And the zero measure set looks like this. So it's everything which is in black. This is a zero measure set, which is a subset of the simplex of parameters L1, L2, and L3. And this set is very loved in Marseille and in the world. Many people thought about this as a set of interesting parameters for different dynamical systems. And its measure is 0, and recent results help us to kind of understand where its Hausdorff dimension is placed. I can say how this set is defined. So the set is defined by some continued fraction algorithm, which is the following. You take your 3 numbers, L1, L2, L3, your 3 lengths. You look if there is one of them which is bigger than 1/2. If it's the case, you stop. You don't go after. You throw away this point from the rosy gasket. If it's not, you take the smallest one of them and you subtract it from the 2 others. Then you check one more time then you renormalize and check one more time if some of the length is bigger than 1/2, and then you continue. And the points that survive this eternal process of exclusion lie in the rosy gasket. One example of such point is the points that I have written here. You see that there are some algebraic properties of points, of periodic points, for example, for this algorithm, which is not surprising. And this particular point is a wonderful point. It's a 3-periodic point of such an algorithm, and it corresponds to an interval exchange transformation, which is called Arnoux-Yukos interval exchange transformation. So it's a square of one of our maps. and it has a corresponding substitution and a beautiful fractal corresponding to it. I won't go in details. It's just to show that this particular point is also very loved and cherished in mathematical community. So I gave you an example, a definition of a parametric family of three reflections. It's one-dimensional dynamics. Now let me come back to tiling billiards, and then I will explain you how this family can be found in tiling billiards context. So as I said, a tiling billiard is a dynamical system that moves a ball through a tiling following this Snell-Descartes refraction law with coefficient -1. For now, of course, I am concentrating on cyclic quadrilateral tiling billiards, but you can imagine any tiling you want, even not periodic, and try to study it. It's a very new system. Actually, I learned about the existence of the system in the same place 4 years ago from Dana Davis. And she was speaking about trihexagonal tiling billiard, so made from equilateral triangles and equilateral hexagons. She was also speaking about triangle tilings. And now we also understand cyclic quadrilateral tilings, and that's all to my knowledge. So it's a very vast field of discovery. So you can just take any tiling and try to understand what happens. For example, for parallelogram tiling, I don't understand what is the dynamics, what is the typical dynamics. But let's come back to our triangles and our cyclic quadrilaterals. What happens, as I said in the beginning of the talk, that all bounded trajectories of such a system are closed. Lots of periodic trajectories, not as usual. So the system is very integrable, one wants to say. Of course, for equilateral triangle, everything is symmetric. So of course, the trajectory will close after 6 iterations. All trajectories are 6 periodic for equilateral triangle billiard. But even if you change the angles of the triangle, it still will be true. Let us see why it's true when we have a neighborhood of some vertex. The explanation is the following, that you can fold, take your 6 sectors and fold one on another. What will happen is that you will fold it like a harmonica, as I said as I showed in the first video, and then it will come back to the same place. Why? Because each second you can color your tiling in 2 colors, yellow and blue, and all the yellow triangles will go left, and all the blue triangles will go right. So the condition for the neighborhood to be folded is that the sum of the blue angles around the vertex is equal to the sum of the yellow angles around the vertex, and it's true in this case. So this local foldability property implies that the folding is well defined, not only along trajectories, but globally. Let me show, so this was a proof. Let me show you the proof in the real life, which actually doesn't always work in the real life because the paper doesn't want to fold if your triangle is acute, but we don't need a proof in the real life for mathematics. So you fold all the plane. You cut out the plane and you fold it. And you see that all the blue triangles go on one side, the red on the others, and the trajectory is folded to itself. And the folding is globally defined, not only along trajectory. This is a property of this tiling. This is not true, for example, for parallelogram tilings. And you see, moreover, that since your 2 triangles are placed in such a way, they form a parallelogram. When you fold one triangle on another, you will find 4 vertices which will be met on the same circle. I actually have a slide for that. Do I? Yes, I do. So you see this picture. So going from tiling billiard on a plane, you come back to the dynamics on the circle, because now your trajectory is moving along a chord in the circle, and the only dynamics is that your triangle is moving in the circle. So this is this idea of the folding, and the picture is taken from the first article on triangle tiling billiards by Brad Smith, Davis, Fromm, and Ayer. Wonderful. So we have the folding. So we know that from the folding, what follows from the folding? That first of all, any trajectory has to pass by each tiling at most once, because to understand where a trajectory goes through a tiling, you just have to look at its image in your folding. And you have a chord which intersects a triangle. It can intersect a triangle only in one place. So from this directly follows that all periodic trajectories all bounded trajectories are periodic, and the periodic trajectories are stable. This folding picture actually also implies the connection with three reflections that I presented to you at the beginning. So here we connect triangle tiling billiards with the family of three reflections that I defined in the first part, because you see the way you place the chord is defined by one parameter. If, for example, it passes by the circumcenter of your tile, tau will actually be equal to 1/2. And then different taus correspond to different placements of the chord. The parameters L1, L2, and L3 correspond to the angles of your triangle. And you pass from one interval of continuity to another when your chord enters a vertex of your triangle. Okay, so you see that why now I need cyclic quadrilateral, cyclic quadrilaterals and not just quadrilaterals, because I need the folding to be well defined. For the folding to be well defined, the sum of these two angles has to be equal to the sum of these two angles. And it is equivalent to the fact that the initial quadrilateral is inscribed. Otherwise, the folding won't be well defined. Okay, so here there is an intermission. Do you have some questions? Okay. So let me show you a small movie of 5 minutes. Sorry? Did it stop? I hope it stopped. No. So let's make a pause. And so in this movie, you will see refraction tilings. And in the end of the movie, you will see how the idea of folding helps you define the parallel foliation on the plane. Because once you have folded, once you know that the folding exists, you now not only have one trajectory, but you also have all the parallel trajectories to it. And you can continue this, this drawing till the end of the plane. At some moment, you will reach the vertex. Here, you will have some singular leaf, and then you will get out of this thing and do some another trajectory, etc. So you will have a foliation of the plane, and the existence of this foliation only follows from folding and the definition of your refraction law. So you will see many of these parallel foliations in the movie. So movie pause. So this was a movie. Do you have any questions after the movie? Sorry? I don't know. It's so this movie was done by Afir David, who is a mathematician now working in Israel, and it's his cat. And the sounds at the beginning of murmuring, it's the murmuring of his cat, but I have no idea what's the name of the cat, but it's the exact coloring of the Afir's cat. Let me also say that in the end, when you have lots of periodic trajectories eating one another, the tiling in itself is corresponding to this fixed point of the Rosy gasket, the Fibonacci tiling. So it's a very special tiling in which any trajectory is periodic except for very exceptional one. So let me state the following theorem. So this we have seen in the movie, we have seen triangle tiling billiards. Let me state a theorem about qualitative behavior of these billiards. So for almost every triangle, no matter which triangle you take, almost always, all of your trajectories will be either periodic, will close up, will be actually simple closed curves, or they will go to infinity in a linear way. They will look as deformed lines. This is a generic case. And very rarely, if you choose your triangle wisely, you will have that any trajectory is periodic, except for those which pass by circumcenters of your tiles. And those trajectories may go to infinity in a non-linear way, and some of them may even fill all the tiles of the plane. And in the movie, in the end, you have seen many, many periodic trajectories. They actually live on the tilings from the point 2. You will have many periodic trajectories starting near the circumcenter, and once you approach the circumcenter in the parallel foliation, your trajectory has a bigger and bigger period, and when it hits the circumcenter, it goes to infinity. So this is a behavior. Almost any trajectory is either periodic, either linearly escaping, and there are these exceptional trajectories which live on exceptional triangle tilings and have to pass by circumcenters of all the tiles they cross. And you see that it's a correct statement, because if I cross one circumcenter, I am obliged to cross another one because of the folding. So this is the distance to the circumcenter is an integral of motion. Okay, so now let me state the analogous theorem for cyclic quadrilateral tilings. For almost every cyclic quadrilateral, the trajectories do the same as on triangle tilings. Either they are periodic, either they go to infinity, escape to infinity in a linear way. And as in the case of triangle tilings, there is an exceptional set of angles, of forms of tiles for which you have a non-linear escaping behavior. So in the case of triangles, I didn't say it explicitly, I think. In the case of triangles, your exceptional set is actually Rosy gasket, the same set as we have seen for inter-exchange transformations, which is not surprising because we have seen that they're connected. This is the same system, more or less. We want to find the same set in the case of quadrilaterals. Yes, I shouldn't have written alpha, beta, gamma, delta. I should have better written A, B, C, D, because these are the parameters that really matter are not the angles of your cyclic quadrilateral, because it's not defined by its angles, but these angles, the internal angles, which kind of correspond to sides, A, B, C, and D. And so we classify the quadrilaterals for which the trajectories may also escape in a non-linear way. And the proof is, there are different steps in the proof. The first step is to understand what is the continued fraction algorithm behind the system. For this, we use renormalization techniques. And then we have to, in order to prove that the measure of the set is 0, and even to prove that the Hausdorff dimension of the set is smaller than 3, we need other methods like the thermodynamical formalism and new results by Charles Fougeron of last year. So it's we need the machinery to prove 0 measure and especially Hausdorff dimension of such an object. I won't tell how it's defined, but I think it's a rather elementary formulation of a statement about the dynamics of cyclic quadrilateral tilings. So I hope it's understandable without a definition of explicit definition of this new gasket. And we call this gasket Novikov's gasket. Let me show you how it looks. The picture is not very good, but you see an octahedron, and there are many holes in this octahedron, many tetrahedral holes. Why octahedron? Because in some sense, when you take a triangle and you exclude the possibilities when L1 is bigger than 1/2, L2 is bigger than 1/2, and L3 is bigger than 1/2, you still get a triangle. But here, when we do it with a tetrahedron and you cut these conditions, you will have an octahedron. And then our more complicated continued fraction algorithm eats some holes inside this octahedron. So let me now explain why we call the set Novikov's gasket, and let me explain how all this cyclic quadrilateral tiling billiards story is related to Novikov's problem, which was formulated 20 years ago, 40 years ago. Here she comes, fundamental mathematics. Okay, so what is Novikov's problem? You take a level surface of a smooth function in T3. And you consider, so you have a surface which lives in a 3 torus. And then you take, you take its covering on in the 3-dimensional space. So you see this surface which looks kind of as a labyrinth. You can think about M being of genus 3, for example. Let me draw it here. So you have your T3. So cube with glued sides, and you, for example, you take a cylinder in it, then you take another cylinder glued to it in another direction, and you glue another cylinder in another direction. So this is a surface M of genus 3. But you can do other much more complicated pictures, and then M hat is a labyrinth of this kind of pieces connected together all over R3. And the Novikov's question was how, what happens if you cut this construction by a plane? So you fix some normal vector, and you consider a family of planes cutting your M hat. In the intersection, you have curves. And the question is, what can we say about these curves? Are they all closed? Are there some non-closed curves? And if they are non-closed, how do they escape to infinity? What is do they have an asymptotic direction? What is if they do? What is if they don't? What is happening, etc. In which speed they are escaping to infinity, etc. So you see that the parameters here are a function that you fix. Then you fix an energy level, so the level of your function. So say we fix the function f, and m is just f minus 1 of E. So E is a energy level of your function. And then you have 3 parameters that correspond to a vector in space, and you have a family of cutting planes. So the motivation for this problem comes from physics, because you can think about this 3-periodic surface as a Fermi surface of some metal in a reciprocal lattice. And you can imagine that you have a constant magnetic field, which corresponds to our vector h1, h2, and h3. And the trajectories, the cuts, the curves that we obtain in a cut are the trajectories of the velocity of your electron. So understanding, answering this kind of questions helps you to understand things about conductivity of metals. So Hennenfent studied this question for a long time, and he has proven the first very important theorem and very beautiful theorem in techniques, topological and Morse theory techniques. He proved that there are three types of behavior possible, and the chaotic behavior is rare. So let me explain what the behaviors are and what I mean by chaotic behavior. So the first case is the following: that if you fix your surface and you fix the direction of your planes, your cutting planes, the first behavior is trivial. All connected components, all the curves in the section are trivial. For example, if I cut this surface with a horizontal plane, the intersections will be just many, many circles. Another case is called integrable case. It's when you can have some compact components, but you also have non-bounding components, but they all look like deformed lines. So you have lines and you have some circles, something which looks like this. Of course, circles are topological circles, so the periodic orbits can be as big as you want. And the third case is chaotic case. It means that the foliation that you obtain on your surface has a minimal component of genus bigger or equal than 3. What do I mean by this? Trivial behavior, you can think about cylinders. If you think about a foliation, you have trivial components, and then when you change a little bit the level of your plane, you will have cylinders that will form. In the second case, when you have deformed lines, it corresponds inside the circles. You see the embedded tori, which have just linear rotations on them. And chaotic case means that your foliation has a minimal component of bigger genus than 2. And Hennenfent has proved that such a third case happens very rarely. What he has actually proven is that if you fix a function and you fix a direction of your magnetic field, then there is only one energy level on which chaotic behavior is possible. You have only one parameter of the energy on which your trajectories start going in some uncontrollable way, and all the other levels actually correspond to periodic trajectories. Okay, but what is, to formulate it differently, the pairs of surface and direction that define chaotic foliations are contained in some subset of codimension 1. And then Novikov has asked, what is the measure of this set of chaotic behaviors restrained to this subset of codimension 1? And there are many conjectures which come from this question, such that the measure of the subset inside this codimension 1 subset is 0, some measuring of Hausdorff dimension. Then you can also fix an energy function. And the last and most interesting for physicists, if you fix a surface, because physicists, they don't care about levels of energy, they want just a concrete surface, Fermi surface of your metal. And there are different conjectures corresponding to it. And here are the two results that exist in the direction of this conjecture. The first has been proven in 2009 by Hennenfent and De Leo, and based on the work of Hennenfent in 1997, that if you restrict yourself to the surfaces of genus 3 with central symmetry, and also with this technical condition of double saddle points, then your chaotic regimes form a measure of 0 subset. And actually, I didn't say it, but it feels like the problem has infinite dimensions, because you can choose any function you want and then try to understand foliation, which is created on it by a family of parallel planes. But actually, it's a finite dimensional problem. And the foliation that is created on a surface can be straightened, and you will only have a finite number of parameters. So in some sense, this first theorem could only work with one concrete function. And this is the surface drawn here is a level surface of this function. And for this function, all the chaotic regimes fall onto one energy level, which is not at all true in the general case. but in this genus 3 two double saddle points case, it's true. And on the right picture, you see the set of chaotic regimes. As usual, it's in white. So you have to get rid of blue, red, yellow, and green. And you see that the set resembles to the rosy gasket as well. And actually, it's exactly the rosy gasket set. A little bit in different coordinates drawn on the projective plane, but it's the same set. So you see that rosy gasket appears in this setting as well. And when we started working on cyclic quadrilateral tilings with Pascal Hubert and Paul Mercat here in Marseille, we wanted just to prove this kind of theorem, so to just understand when trajectories can escape in a chaotic way. We understood how to prove the first part using renormalization, and we were trying to find the answer to the question 2. And at the same time, parallelly, Sasha Skripchenko and Ivan Dynnikov in Moscow, they were thinking about the same question in terms of Novikov's problem. And today we have the result, which proves the analogous result to Dynnikov-DeLeo case, but getting rid of two double saddle points. So we just have a genus 3 surface, which is centrally symmetric, and we prove that chaotic regimes form a measure 0 set in this subset of chaotic regimes found in Dynnikov's theorems. So let me say that centrally symmetric case is very important for our work and our proofs, but one can say that it's okay because Fermi surfaces are always centrally symmetric, so it's a meaningful case for physicists. And genus can be made higher, indeed, but in some sense also genus 3 is the simplest one and the most interesting for physics, because for higher genus, probably chaotic components will still be concentrated on genus 3 surfaces. So this is our result, and actually what I want to say is that this result is exactly the same result as a theorem about behavior of cyclic quadrilateral tiling. So this is one theorem and this is another, but this one is another, but this is the same theorem, just reformulated in two different languages, one of tiling billiards and another of Novikov's problem. So let me maybe say how tiling billiards relate to Novikov's problem, because I explained you the connection between tiling billiards and inter-exchange transformations. It's not very difficult. It's just coding and looking what system you obtain. Although the connection between points 2 and 3, it's a little bit more intricate. This slide kind of explains the connection, how you go from a cyclic quadrilateral tiling billiard to a surface which enters the setting of Novikov's problem. The inverse direction is more technical, but it also can be done. So in some way, cyclic quadrilateral tilings are an elementary model to study Novikov's problem in genus 3 in the centrally symmetric case. So how much? I don't have. I have 2 minutes, right? So let me say that how can we do it? So we have a tiling. Let's say a triangle tiling, because the construction is more or less is exactly the same. So we want from a tiling to construct some surface that will go into Novikov's problem paradigm. The surface, as I said, we want it to be a level of some function. So let me first say that the energy here is exactly the distance till the center of the circle. Let's say energy is 0 when we pass by the circle, and then it goes up, or it goes down if we go in another direction. So change of direction is changing the sign of the energy. So let us fix some energy. For example, as drawn here on this picture, fixing the energy is saying that all our trajectories have to start tangent to some circle which has the same center as a circumcenter of our triangle. Take them all these trajectories. Here there are 3 representatives drawn in red. They all intersect in one triangle. So what we will do now, we will just lift them up as a helicoid, and you will obtain in this one triangle just a helicoid. Yes, we obtain a stairs going like this. You can do the same in the neighboring triangle. And the idea is that you can do it everywhere on all the plane, and you're constructing a surface in such a way. It's obviously periodic in a vertical direction, but from the folding, what follows from the folding, that this surface has two more periods, has two more space periods. And so here I have constructed actually a fundamental domain of the surface, and then you draw it in all directions, and you enter in the Novikov's problem paradigm, because the horizontal sections of your surface are exactly tiling billiard trajectories, and we know that they are almost always periodic or linearly skipped. So this is a simply explainable connection from one side to another. Going in another direction is more complicated, and you see that for triangles we have a good number of parameters, because we have 3 parameters of a triangle, and they correspond to the direction of the plane which is making a section of your surface. In the case of cyclic quadrilaterals, it's more difficult, because you have 4 parameters of a cyclic quadrilateral. So the same cyclic quadrilateral corresponds to different functions. So this is you have to separate a surface, a fixed function, from anything else. And this is what makes the study of Novikov's gasket in particular more complicated. But this is the idea. I hope that I gave you a sense of how tiling billiards are related to some problems in topology. And I thank you very much for your attention.
Are there any questions?
Thank you for the talk. I have a comment, not a question. It's a unique situation. This subject started as an undergraduate research project at Institute for Experimental Mathematics at Brown University, 2 consecutive summers, 2012 and 2013. So the students were asked to experiment with tiling billiards with Penrose tiling. This is probably will be much more complicated than what we saw, but they, of course, wanted to start with simpler shapes, such as triangles, and I think there was a tiling of hexagons and triangles also. And the way we learned about this problem was from physicists. I actually received an email from a physicist whose name I don't remember now. He said that these materials can be made today with the negative Snell coefficient. And it's very important for optics. No comments why it's important, but apparently they make better lenses using this technology. And he asked whether mathematicians can describe anything like periodic trajectories. So the problem really originated in real life. And now I'm very happy to see that deep mathematics also related to Novikov's conjecture. And if anyone wants to experiment, Penrose tiling is an interesting example. I'm very curious what happens. Thank you.
Yes, thank you very much for the comment. Indeed, I didn't mention everybody, and I'm sorry for that. So, for example, these pictures come from the program that Pat Hooper and Alex Saint-Laurent made, I think, following one of the summer schools. And considering Penrose tiling, maybe, I don't know if Diana is here, but I remember that several years ago when she told me about Penrose tilings, she said that they have seen many periodic trajectories on Penrose tilings. But I don't know where it went from there. But yeah, who knows?
Okay, any other questions? Before we thank this, there's a question? Okay. While I'm bringing it, there's an announcement that there'll be a problem session at 5:45 for anybody who's interested.
So I was once thinking about the problem leisurely, so I didn't do anything, but it seems like to have the same spirit. So you take a periodic function of 2 variables and a linear function, and so the question is level curves. So the intersection of that surface, of the periodic surface with the plane that is slanted? And do you have a level curve that goes from infinity to infinity as a function of slope and direction? So there is a rationality probably involved. So that's an interesting question, I think, maybe related to this.
Yes, I can't answer that, but what I can say is that in general, the study of quasi-periodic functions has been initiated by Arnold, and I think here we have one context with 3 periodic functions and sections by planes, but I think different dimensions were studied also by Novikov and Hennenfent, so maybe the answer to your question already exists. But
Thank you. Any other questions? Okay, then let's thank our speaker again.
thank you.